Hello, good morning, Dr. Nat here. So this is lecture number 2, part 2. Okay, part 2 So this is measures of variability. We're going to talk about that. Previously, we talked about measures of center. We found out that the mean is not actually reliable when the data is not symmetrical, right? So the mean can be smaller or bigger than the median and a not accurate measure of center. Okay, so now we're going to talk about measures of variability. So what is measure of variability? It is a measure along the horizontal axis of the data. So this is the horizontal axis of the data distribution that describes the spread of the distribution from the center. So here we have a symmetrical distribution, right? So we are going to assume that our center is over here because that looks like it. So the distribution from the center is this much and this much. I don't know how much that is, but that is how it looks like. And if we have this type of distribution, it is also symmetrical. This is our center, and there's only like two datas from the center. So we have two data from the center in the negative side and two data from the center in the positive side. So compared to this one, we have 4 and 4. So the variability is larger over here compared to this one. Okay, we're going to talk more on that one. Okay, so what is range? I told you that range is the difference between the largest and the smallest measurement. For example, if you have this data set, you need to find out what is your maximum, this is your maximum, and what is your minimum value. Your minimum value here is 5. So your range will be 14 minus 5, which is 9. 9 is your range. Range is denoted with capital R. Okay, so previously I told you that the average is an X with a bar, and this symbol over here means sum. And XI, X refers to your data, I is your set number. For example, 5 is X1, 12 is X2, 6 is X3, 8 is X4, and so on. So this is the sum of your data over your number of data. So your number of data here is 5. Your N is 5. Okay? So just recapping some of the things that we already covered. Moving on. So next is the variance. The variance is a measure of variability, the word again, that uses all the measurements as opposed to range that only uses 2 measurements. Remember, the range only cares about the maximum and the minimum. It doesn't really care what's in between. So if your data is like 1, 1, 2, 2, 3, 3, 4, 4, and suddenly you have an extreme value of 50, suddenly your range is what? 50 minus 1, that is 49. But in reality, most of your data is just between 1 to 4. So this range is not really accurate, even though the definition is correct, but it doesn't really represent your data well. Okay, so that's my point here. Okay, so let's look at this data. So here they have given us that the average for this data is 9. 5, 12, 6, 8, 14. The total is 45. The number of data here is 5. 45 divided by 5 gives you a mean of 9. So 9 is over here. Okay, so again, this is our center, and our distribution is this much and this much. Now this tells me that the data has a large deviation from the center compared to a data that looks like this. Let me give you an example. So this is my line over here, same values, 4, 6, 8, so on. Let me just put that here really quickly. 4, 6, 8, 10, 12, and also 14. And my center is over here, same center, but my data is more over here instead of like distributed like that. So here I can see that for this data set, my deviation is small, whereas this guy over here has a larger deviation. Okay, so it tells you how far your data is from the center. If your data is far away from the center, your deviation is large. If your data is closer towards the center, your deviation is small. Okay, so we have two equations here. The variance of a population of n measurements is the average. Okay, what does average mean? Remember, the equation for average is this guy over here. So basically, you are dividing your sum of data divided by the number of data. So here they are telling us the average of the squared deviations. So we have the average over here, we have a sum of the data, and we have divided by the number of data. So it kind of looks like this, so it's an average. But on top of here, it says that it must be a squared deviation of the measurement about their mean m. But here we don't have an m, we have a mu. So this is actually a mu. Okay, your mu is your mean lah. It's your mean. Okay, so let's relate back to the data that we saw earlier. So we have this data 5, 12, 6, 8, 14, right? 5, 12, 6, 8, 14. Let me write that down because I can't remember. 5, 8, 6, 14. What am I missing? 5, 12. I missed out 12. Okay, so how do I put these values inside my equation? Let's do it. So our mean was given as 9. Remember, they already calculated it for us, so we're just going to use this as our mean. Okay, let's go back to this one. So this one is the variance of the population is equal to the sum, which means that I have to add up all these guys together. So 5 minus 9 squared plus, let's get rid of the sum because I'm going to put in the positive sign here, sorry, the add sign here, and then 8 minus 9 squared, and then I have 6 minus 9 squared, and then I have to add 14 minus 9 squared, and then I have to have 12 minus 9 squared. What does this represent? It represents the sum of the data minus the mean squared. The data minus the mean squared, and you have to find the sum of it. So, and then you have to divide it by the number of data that you have, which is 5. So this is your variance population. So let's calculate and see what the answer should be. So 5 minus 9 is 4, so it's a 4 squared plus 1 squared plus 3 squared plus 14 minus 9 is 5 squared. What is this? This is 3. And then we have 12 minus 9 is a 3, so that's a 3 squared divided by 5. So 4 squared is a 16, 17 plus 9, 26, 26 plus 25, that should give me 51, 51 plus 9 is a 60, 60 divided by 5, that should give me a 12. So my population variance is a 12. My population variance is a 12. Okay, so now we have a second definition. The variance of a sample of n measurements is the sum of the square deviation of the measurement about their mean. Kind of sounds the same, right? Divided by n minus 1. Now why is it different? Why is it called S? And why do we have the n minus 1? If it's supposed to be the average, shouldn't it be just n? But here, the definition doesn't mention average. Okay, it just says divided by n minus 1. Okay, so before we get to this why we have the n minus 1, I have to tell you what sample is versus a population. So let's head on to that. So variance of a population versus variance of a sample. What does a population mean and what does a sample mean? So for example, a population is engineering graduates. Anyone that graduated with an engineering degree is considered as an engineering graduate. It doesn't matter if you're electrical, if you're a communication engineering graduate, if you are, what else do we have? Mechanical engineering graduate. All of those are considered the population of engineering graduates. But the sample will be a sample of the population would be engineering graduates of the year 2021 only. You have a lot of batches, right, that graduate. You have engineering graduates of 2021, you have engineering graduates of 2020, you have 2019, 2018, and back to when UPM was established, which was, I don't know, 1970 something, I don't know. You have those batch. You have a lot of engineering graduates. So that is your population. But when you take that whole population of data and you only take a small chunk of it, this is your sample. This is your population. Your population is engineering graduates. Your sample is only a subset of that population data. It can be anything. It doesn't have to be engineering graduates of year 2021. It can be specifically engineering graduates from mechanical department. So that is a subset of engineering graduates too. It can be chemical engineering graduates from the engineering of UPM. So that is your subset of a population too. Okay, so that is sample versus population. Now when we take sample and we want to find the variance, obviously the sample is just a small chunk out of the big data, right? We have a lot of data here, but we're only taking this small chunk. Will it be accurate to represent our data, to present our data accurately? The answer is yes and no. Because we're only taking a small chunk, we can't actually find the average, right? We can't use the average definition here because the sample only takes a look at a small number of data versus the population. Maybe the population is thousands, but the sample is only like 20 data. So it's not very accurate if we want to find the mean, just like the population variance. So what they did is to correct this inaccuracy, they introduced this n-1. This n-1 is called the Bessel correction. Bessel correction, Bessel correction. So what is Bessel correction? Bessel correction is basically the act of dividing this guy over here by n-1. What do you get when you divide it by n-1? It corrects the biasness that you get from just taking a small chunk of data out of a very, very big data. So it corrects the biasness. So this approximation actually works. I don't know how it works, but it works. Okay, so that was what they came up with, the mathematicians, right? So we're going to follow that. It's called the Bessel correction. Do you have to remember the name? Not really. I'm just introducing it to you guys. Okay, moving on. So let's go over an example for variance. So example for calculating sample variance. Again, when we're talking about sample variance, we're only taking a small chunk out of a huge data. So the huge data is our population and our small data is our sample. Sample is always the smaller guy. Sample is a subset of a population. Okay, so suppose a botanist wants to calculate the variance in height of a certain species of plants. Okay, so I was assuming the gender here, so let's just say it's a she. So she said, hey, I want to know the height of the plants in this region, but I only want to calculate for this sample, because obviously there are thousands of plants in this region and I don't have time to measure all of them. So I'm just going to take a sample of 20 plants from this region. Hopefully it gives me the right idea about the other plants, I mean the thousands of plants. Okay, so because there are thousands of individual plants in one region, she decides to take a simple random sample of 20 plants. Again, because sometimes we can't measure all of the data, right? So we take a small chunk only. So 20 plants is a subset of the thousands of plants in that region because it's a sample of a population. In this scenario, the botanist should calculate the sample variance. She should not use the population variance equation because that would be not correct. Remember, the population variance is the average. It has that over n, versus when we're talking about sample variance, we have that correction, the Bessel correction, which is very important when we're only taking a small set of data from a huge data set. So she should use the sample variance because she is interested in the variance of the entire population but is only using a sample size. Okay? Next. So here we have 20, I think this is 20 students here. Suppose a teacher wants to calculate the variance of exam scores for the 20 students in her class. Okay, she wants to calculate the exam scores. So in this scenario, the teacher should calculate the population variance because this is her data. The data is the population itself. It's not a chunk of some other data, it is the actual data. So she can use the population variance equation. Because the data set she's working with, which is the 20 exam scores, represent the entire population that she is interested in. So she should use the population variance equation. Okay, so we talked about variance, and variance was, for the population variance, it was this guy, and the sample variance was this guy. Okay, let me go back to sample variance because I think I did not explain it in depth yet. So this is the sample variance. We denote it with S squared. It has to have that squared. The squared is important. Without the square, it is not correct. Okay, so for sample variance, you have that Bessel correction. And this guy over here on the top is still the same. It is your data minus the mean of your sample. This one is your mean of sample. This guy over here is the mean of your population. That's why they have a different symbol. But in reality, they are both mean. Okay, so this is your data and this is your data. This is the sum and this is the sum. Actually, everything else is the same except this symbol over here and the Bessel correction. So please take note of that. Okay, mean of your sample. Okay, so that is the difference between the two equations. So going back to this guy, I told you about variance. We have the population. We also have the sample. Okay, so this is called variance. Variance, right? We have another name which is called the standard deviation. The standard deviation is basically the square root of the variance. So if we're talking about population standard deviation, we square root the population variance. And when we're talking about sample standard deviation, we are going to square root the sample variance. It's basically the same thing but with the square root. So you have two terms here. One is standard deviation, the other one is variance. Please distinguish between the two. Don't get confused, okay? Okay, so I'm going to introduce two ways to calculate the sample variance. So the first one is the definition that we talked about earlier. So this is sample variance is equal to the sum of the deviation squared divided by n-1, or the Bessel correction. Now here is our data 5, 12, 6, 8, 14, the same data that we've been talking about for this topic. So the mean was 9, right? We were given with this value, the mean was 9. So 5 minus 9 is minus 4, 12 minus 9 is 3, 6 minus 9 is minus 3, 8 minus 9 is a minus 1, 14 minus 9 is a 5. So this is your data minus mean value. Then you have to square it. So this is the square values, and then you have to sum it. This is what you're trying to find out here. So this is going to be xi minus mean of your sample squared. So the total is equal to 60. So 60 is over here. And then your data is 5, which means that n-1 will be 4. So 60 divided by 4. Okay, so 60 divided by 4 will give me 15. So my sample variance is 15. And to find out what is my sample standard deviation, I have to square root that. And the square root of 15 is 3.87. So S is my standard deviation, sample standard deviation, whereas S squared is my sample variance. So it's the same formula, but you have that square root coming. Alright, so the second way to calculate the sample variance or the sample standard deviation is to actually first find the square of your data, the sum of the squares of your data. So the sum of squares for your data is 25 plus 144 plus 36 plus 64 plus 196. That gives me a 465. So this is a 465 minus with the sum of your data square. So that's different. The sum of your data square. So your data is 45 and you square this guy. So this is a 45 squared. So 465 minus 45 squared divided by n. N is 5. This is 45, right? And then divided by n-1, which is 4. So here we have 465 minus 45 squared divided by 5. This is your n. Divided by the Bessel correction, which is 4. So you will get the same answer, which is 15. Now, is this going to be easier or is this going to be hard? So let's compare. So if my data is like only 5, right? We only have 5 data here. So I can just, do this method, no problem. But what if I have like hundreds of data? Is this going to be a feasible way to, calculate my sample variance? I don't think so. So when you have a large set of data, this method is preferable because basically you just have to find out what is your sum of data squared and also this guy over here. You don't have to you can already see that you have minimal calculation versus this guy. You have like 3 columns. Here you only have 2. So obviously you're already cutting down time. Okay, so depends on the number of data that you have. You can choose whichever that you want to use, but for large data I would recommend to use this equation, even though it's kind of hard to remember. But the internet is free, so just Google the formula. Okay, moving on. Some notes. The value of S is always positive. Why is that? Why was this emphasized? Okay, so let's take a look. S squared is your variance, right? And to find out the standard deviation, you have to square it. When you square something, remember you can get a positive or a negative value. For example, if I'm squaring 4, I can say that the answer is plus minus 2. gives me 4. Positive 2 squared also gives me 4. So the square root of 4 is actually, it can be positive or minus 2. But here, they are emphasizing that s should always be positive. So please take note on that. Don't give me a negative value for s. So the larger the value of s squared or s, the larger the variability of the data set. I talked about this early on. This is your center. It means that it is more far away when your variance is bigger ataupun sample variance is bigger. But when your data set is closer towards the center, only like a small arrow like this, it means that your sample population variance, your population variance or your sample variance is smaller. Okay, so the sample standard deviation S is often used to estimate the population standard deviation sigma. Dividing by n-1 gives us a better estimate of the sample standard deviation. It eliminates the biasness, and the act of dividing it by n-1 is called the Bessel correction. So this is your exercise. Please take a screenshot and try to do it yourself. I'm going to give you the solution on WhatsApp later. Okay, so the number 1 question is find the mean, median and mode of this data set. Number 2, eliminate the last observation x25, which means that it's telling you to get rid of this, so your data set is just 5 to 6 over here. And then find the mean, median and find the new mean, median and mode. How do these values compare with those found using the full data set? So it's asking you, hey, compare the mean, median and mode between number 1 and number 2. Then number 3 question is, how do possible outliers such as 25 affect these values? Remember, I told you if we have extreme values, who is most affected, who is not affected? Do you remember that? Next, exercise number 2. Okay, so this is your data. Calculate the range. Remember, the definition of range is maximum minus minimum. And then find out the mean. What is the definition of mean? And then find out the variance. We have, usually for a small set of data, we are assuming we are taking this from a huge chunk of data. So typically, when we're talking about variance, we use the sample variance equation. And then same goes for the standard deviation. We're going to use the sample standard deviation. Now, use sample when your data is small unless it tells you specifically that this data, that this small number of data is actually the entire population. Then only you use the population equation. Okay? So before I end lecture number 2, I would like to give you this quote. Every day may not be good, but there is something good in every day. So try to find something good in your day. Have a great rest of the day, and I'll see you in class. Bye-bye. Take care, everyone.